Folks, welcome to the next episode of Electromagnetism. Today we're going to continue our discussion of the spherical Laplacian. I'm going to walk you through step by step through two problems where we determine the electric potential using the spherical Laplacian. I'm going to go step by step, no step skipped. So if you have any questions at all, leave a comment down below and let's get to it.
I'm trying to make something good out of nothing. I just want to make you proud someday. Take a ladder to the moon, hands to the ceiling, feeling like the world finally turned my way. And it feels so good.
So let's begin at the beginning, which says that the divergence of the electric field is the volume charge density over epsilon naught. This right here is Gauss's law. It basically tells you if you know how much of the electric field penetrates a certain Gaussian surface, then you should know how much charge is inside that surface. Now from this, we also had another formula, which was that the curl of the electric field is 0. From this formula, we got that the curl of the electric field being 0 admitted a scalar potential for the electric field. And that scalar potential was defined as minus the gradient of the electric potential gives you the electric field. And furthermore, we can say something else. Now that we know that the electric field is minus the gradient of the electric potential, we can plug this back in for E over here. And look what we get. The divergence of, instead of E, I'm going to write minus the gradient of V is minus rho over lambda, rho over epsilon naught, there's no minus yet. And then the divergence of the gradient is going to give us minus the Laplacian, this minus sign comes from here, of the electric potential is the volume charge density over epsilon naught. And then we can just move the minus sign to the other side, which gives us Poisson's equation. The Laplacian of the electric potential is minus the volume charge density over epsilon naught. This right here is Poisson's equation. And in fact, we have solved Poisson's equation for the electric potential previously. In fact, it was one of the first things we did to find the electric potential. I did not derive it in the videos per se, but the electric potential, when you solve for Poisson's equation, is 1 over 4 pi epsilon naught times the integral of the volume charge density times the integrated over the entire surface over how far away you are from where the source charges are and where you want to determine your electric potential. So the picture that goes along with this is that you have some kind of a arbitrary charge distribution having a volume charge density rho that might vary depending on where you are. We're integrating over this entire region, and let's say we want to determine the field somewhere here. This R on the denominator is that R right there. So this is the electric potential when you solve for Poisson's equation. But what happens if you don't know the volume charge density? For example, if you're looking at a conductor, you might not know how the charge distributes itself over the surface or throughout the object. In that case, if you have an area that has region that has no charges, then Poisson's equation becomes Laplace's equation. So the right hand side becomes 0 if you're considering a space that has no charges. That doesn't mean the electric field or the potential is 0. It just means that the region you're looking at is 0, has no charges. So this right here is Laplace's equation. Laplace's equation. And we solved this equation in rectangular coordinates by assuming that the electric potential was separable as a function of x and a function of y, right? And then we plugged it back in here, and then we got this second order partial differential equation or ordinary differential equation. And we figured out, okay, if these two add up to be 0, but they're functions of different variables, that means they must both be equal to constants, C1 and C2. And so we eventually figured out that implied that these two functions either have to be exponentials or oscillating functions, and which one they were depended on the boundary conditions. So we would choose what type of functions they are, x and y, depending on the boundary conditions, and then we would write out Okay, v is some linear combination of these two functions, x of x and y of y, whatever they may happen to be, from m equals 1 to infinity. Okay, and this is the expansion coefficient, which we would determine using Fourier's trick afterwards. So that was the whole procedure for rectangular Laplacian. In the previous episode, in just the last episode, we saw how to solve the electric potential in spherical, for the spherical Laplacian. So how do you solve Laplace's equation in spherical coordinates? Let's check that out. So to solve Laplace's equation in spherical coordinates, we have to do the same idea, apply the idea of separation of variables, and assume that the electric potential is made out of a function. So we separate v as a function of a radial component, an angular component, and as a mutual component, something like this. But of course, in undergraduate electromagnetism, we don't deal with the phi hat component. And then you plug it back in here and you do some math, and eventually you end up with the following solution for the Laplacian and spherical coordinates, which I'm not going to derive, but I will motivate it. It is a sub l r to the l plus b sub l over r to the l plus 1 times the legendary polynomials p sub l cosine theta. Okay, let's go through this step by step, where L starts from 0, heads to infinity. Let me motivate each one of these terms right here. In the previous lecture, we saw that this was the basis set, the ingredients for creating any desired electric potential. Let's see how that works. We saw that if L equals 0, then this term is just a 0. And if L is 0, then P of 0 cosine theta is just 1. So all you have here is a constant potential. So this right here is a constant potential. And that can be adjusted to match any field you'd like. But what if it's not L equals 1? If L is not equal to 1, if L is not equal to 0, then what would happen? Well, let's see. If L is equal to 1 instead, so if L is equal to 0, we just have A naught. But if L is equal to 1, then we would have A sub 1 times R times cosine theta. Right? Since P sub 1 of cosine theta is cosine theta. Recall your legendary polynomials from the previous episode. So, what is this? What kind of potential is this? Well, for L equals 1, we get the potential for a constant electric field. Right? So this right here, A sub 1 R cosine theta, that's the potential for a constant electric field that may be pointing up or down the z-axis. So for example, let's say you have an electric field that's going straight down the z-axis. Okay? Then, and it has a magnitude of E sub 0. Then the electric potential for that will be minus E sub 0 z. Right? But of course it's heading downwards, so that would mean it's just E sub 0 z. And z in spherical coordinates is r cosine theta. Right? So that's what you have. You have the electric potential for a constant electric field. Okay. So far our claim is holding up to scrutiny. Now what if L equals 0 for this one? In this term, if L equals 0, we're going to have B sub 0 over R times P sub 0 of cosine theta, which is just 1. So what we have here, what you're looking right there, is the potential for a point charge, right? It's the potential for a monopole. So for L equals 0, we get the potential for a monopole, V for monopole, which is just a fancy way of saying a single charged particle, right? And what if L equals not 0, but 1? Well, in that case, we would have B sub 1 over R squared cosine theta. Well, what is that? But, as we explained in the previous episode, that is the potential for a dipole, right? So this is going to be L equals 1 is the potential for a dipole. So hopefully you see what's going on here, right? You can see that these two terms that make up the spherical Laplacians, the solution of the electric potential in spherical coordinates to the Laplacian equation, these two terms are just giving you two different pieces of the puzzle. One term, the first term right here, the term that is linear in R, is giving you all of these things. It's giving you the constant potentials. It's giving you the constant electric fields. So it's giving you the boilerplate stuff that you need to create any desired electric potential. Now, not constant electric fields, but the electric potential for constant electric fields. And the second term right here, the term that is inversely proportional to the Lth plus 1 power of R, this term is giving you the potentials for the monopoles, for the dipoles, right? When L equals 0, this gives you the monopole potential. When L equals 1, it gives you the dipole potential. And when L equals 2, it'll give you the quadrupole potential, right? That's 4 charges situated like this, plus, minus, minus, plus, connected to each other as such. And for the L equals 3 term, you'd get the octopole potential, right? Which would be a cube of charges, like this. So really, that's the idea, okay? All you're doing is that you're adding up the boilerplate stuff, the constant potential, the potential for a constant electric field, and you're adding the monopoles, the dipoles, the quadrupoles, the octopoles. So that's really what you're doing here. So hopefully that gives you a sense of why we have what we have. And furthermore, if you watched the previous episode, you would have seen why we need a term that is linear in R and inversely linear to R, R to the L plus 1. Why is that? Well, when you're considering the potential inside an object, for example, inside a sphere, then the potential, you can't let the potential go to infinity, right? So this term, as R gets smaller, as you approach the origin of this sphere, R will get smaller, and hence this second term will get bigger. But this term will be just fine. This term will just approach 0, right, as R gets smaller. But this one will head off to infinity. So you can discard this term for potentials inside spherical distributions. On the other hand, if you're looking outside the sphere, if you're heading off to R equals infinity, then this term is going to diverge to infinity, right? As R gets bigger, R to the L will of course approach infinity. So you can discard with this term and instead stay with this one, this second potential term. So that's, you can see all the kind of motivations behind the structure of this equation. The first motivation is that you're adding the boilerplate stuff, your constant potentials, your potentials for constant electric fields, to your monopoles, your dipoles, your quadrupoles, your octopoles. On the other hand, you can also motivate this by saying, okay, how do I get the electric potential inside a spherical conductor, for instance? Well, I'm going to have to consider the first term, because the second term is going to diverge. And how do you, what if you're considering the electric potential outside of your spherical conductor? Well, then you're going to have to consider the second term, because the first term is going to diverge as R heads off to infinity. So there's all these kinds of things playing in, but those are the two big motivations for why the solution to Laplace's equation in spherical coordinates looks the way it does. Now let's take a look at our first problem. Here is another view of problem 1. Okay, so here's the problem we're considering. The electric potential on the surface of a sphere of radius A is given as B plus gamma cosine theta. Assume that there is no charge inside or outside the sphere, only on the surface of the sphere as a surface charge. For part A, we have to find the potential inside the sphere. Okay, so let us begin with the formula for the solution to the Laplacian equation in spherical coordinates. So that formula tells us that the solution to Laplace's equation in spherical coordinates is v of r comma theta is L, the summation from L equals 0 to infinity of my boilerplate terms plus my dipole, monopole, quadrupole, octupole terms, and of course my legendary polynomials right here. Okay, so these are the background characters, the foreground characters, and my supporting character. So now, what is the potential inside going to be? Well, remember, the essential idea for the electric potential inside, V inside, aka R is less than A. In that scenario, we would like to prevent the potential from diverging as R approaches 0. Now, as R approaches 0, as we get closer to the center of our sphere inside, notice that this term gets smaller. So A sub L, R sub L, the boilerplate term, gets smaller, but the main term, the main actor, the protagonist, the monopole, dipole, octupole, quadrupole term, this term is going to diverge. It's going to head off towards infinity, because as the denominator gets smaller, the fraction is going to get bigger. It's going to explode, right? So, and B sub L over R to the L plus 1, that's going to diverge, right? And so we have to prevent that. How do we prevent that? Well, just chuck this term away. We don't need it. So in other words, this leads us to conclude that B sub L is 0 for all L when we are inside the spherical charge distribution. Okay, so that means our electric potential inside is simply going to be the summation from L equals 0 to infinity of A sub L, R to the L, times P sub L cosine theta. Okay, well now I can go walk to the surface and use that boundary condition to figure out what A sub L has to be and what terms I'm going to need from this. So I'm going to walk to the boundary. In other words, I'm going to set my radius to A, and in that case R is going to change from R to A, right? So I'm going to have the summation from L equals 0 to infinity A sub L, but now instead of R to the L, I'm going to have A to the L, because I'm now at the surface of my spherical charge distribution, times PL cosine theta. And what does this have to equal? What is the electric potential at the surface? Well, I'm given that. It's beta plus gamma cosine theta, right? It's beta plus gamma cosine theta. Well. Look at what we have here. Perhaps it's not obvious, but I'm going to go ahead and write out the first few terms of this summation. I'm going to expand the summation, show you the first few terms, and then maybe you can realize what's going on. So the first term of this summation is when L equals 0. So I'm going to have, expanding this out, what am I going to have? I'll have A sub 0 times A to the power of 0 times P sub 0 cosine theta. I'm not going to skip any steps so that you see what my thought process is, what I'm going through. Plus, now I'm going to write the L equals 1 term. This is the L equals 0 term. So A sub 1, A to the power of 1, P sub 1 cosine theta. And this is my L equals 1 term. And all of this is equal to beta plus gamma cosine theta. Notice that there's 2 terms here and 2 terms here. So we can set them equal after we simplify a bit. Now, of course, A to the 0 is simply 1. Anything to the 0th power is 1. The 0th legendary polynomial is simply 1 as given here. And so for our first term we simply have A naught is equal to beta, right? Or let me simplify it a bit and then we'll get through it. Now A to the 1, well, that's just A And p sub 1 cosine theta, the first relation of that polynomial is just going to be cosine theta. If you're wondering why it says x here, it says p sub 1 of x. And here we have p sub 1 of cosine theta. Since x is cosine theta, p sub 1 of cosine theta is simply going to be cosine theta. So what are we left with? We're left with a sub 0. Hopefully you can still see down here. A sub 0 plus a sub 1 a cosine theta is equal to beta plus gamma cosine theta. Now we can make the comparison. Notice that a0, a sub 0, and beta are going to be equal. Right, so let's write that down. A sub 0 is beta. Okay, what about a sub 1? Well, a sub 1 times a cosine theta is gamma cosine theta. These cosine thetas match, hence this a sub 1 times a must match this gamma. So let's write that down. These two guys match right here. So that means a sub 1 must equal, since we have a sub 1 a cosine theta is gamma cosine thetas cancel out. Right, let me write it down explicitly. We're just comparing these two terms. The cosine thetas cancel out, so we're left with a sub 1 is gamma over a. Right, nothing too crazy. So a sub 1 is gamma over a. Well, now that I've figured out a sub 1, I can go ahead and go all the way back and plug it in back here and figure out what my final electric potential inside my sphere is going to be. Okay, so what is our electric potential inside? Well, it's simply going to be, let me write it down here, V inside, which is R less than A, is going to be the first term, A sub 0, which is simply beta, plus the second term, A sub 1, which is gamma over A, times R cosine theta. This right here is our final electric potential inside our sphere. If you're wondering, why did I write it like that? How did I know that that was going to be the electric potential? Well, remember that the format for the electric potential inside is simply going to be a sub 0 times a to the 0 p sub 0 plus a sub 1 a to the 1 p sub 1. Of course, a sub 0 and p to the 0, those are just 1. I can just disregard them. A sub 0 is beta, a sub 1 is gamma over a sub 1, this should be r to the 0. R to the 0 and r to the 1. That's where this r comes from. And p sub 1 is of course cosine theta. So that is where this answer comes from. So this right here is the electric potential inside our spherical charge distribution. Now let's find the electric potential outside the charge distribution. Okay, so what can we say about the electric potential outside our spherical charge distribution? Well, outside our sphere, what's going to happen is that this term, what used to be the nice term, is now going to diverge. As r gets farther and farther out, as we go farther and farther out from our sphere, this first term, our background term, our stage term, the term that has our constant potentials, our potentials for our constant electric fields, this term is going to diverge. Whereas this term, the bad term, the term that, not bad term, but the term that was bad inside, that used to diverge, this term is going to be perfectly fine. It's going to go ahead and converge to 0. So this is the bad term in this case, right? Because I don't want to use bad term, but this is the term that diverges when we go outside, very far away from our spherical charge distribution. So we're going to have to chuck away this term. We don't need it. And so the the electric potential outside Vr greater than A is simply going to consist of our second term, the term that has our monopoles, our dipoles, our quadrupoles, our octupoles. It's just going to have this term. So we're going to have the summation from L equals 0 to infinity of B sub L over R to the L plus 1 P sub L cosine theta. And now what we're going to do is apply our boundary condition. What is our boundary condition? It's that when we go backwards, when we come over here, then we have this electric potential. We know this. This is what we're given. If we're right at the surface, not all the way wherever, but right at the surface, then our electric potential should be beta plus gamma cosine theta. So let's impose that boundary condition. So we're going to have when the electric potential outside, R greater than A, is confined to the surface, then my electric potential should be exactly this, beta plus gamma cosine theta. And of course that's going to equal this, but where R is set to A. So I'm going to have the summation once again of from L equals 0 to infinity of capital B sub L over not B but rather A to the power of L plus 1 times PL cosine theta. And now we can play the same game, right? We don't even have to use Fourier's trick, which would be much more time consuming, by the way, but you could nevertheless do it. So instead, what we're going to do is just expand out the first few terms of this by noticing that we only have two terms here. One of them has a cosine theta. So this is a dead giveaway that only the L equals 0 and L equals 1 terms will be left over. So let's go ahead and expand this term right here, expand this summation. So the L equals 0th term of this summation is going to be B sub 0 over A to the power of 0 plus 1 times P sub 0 cosine theta. As you can see, I'm not skipping any steps, I'm not doing anything quickly, just so you can see what I do. Okay, and then the L equals 1 term is going to be P sub 1 over A to the power of 1 plus 1 P sub 1 cosine theta. And all of this is going to equal beta plus gamma cosine theta. Well, okay, now I can simplify matters a little bit, take things onto my own hands. I know that P sub 0, the first or 0th legendary polynomial, is simply 1. A to the power of 0 plus 1, that's just A, right? So I don't have to include all of this mess. A to the 1 plus 1, well, that's just A squared right here. And my first legendary polynomial, P sub 1 cosine theta, is simply cosine theta. So now, rewriting and consolidating everything I have into one piece, I'm going to have beta plus gamma cosine theta is equal to B naught over A plus B sub 1 squared, B sub 1 over A squared cosine theta. And now is when we do the mix and match, okay? Notice that this term and this term are going to be mixed together or matched together. I'm not going to match these two terms because this has a cosine theta, whereas this doesn't. So I know that this term must match up with this one. So these two guys match. And now just set those matching pairs equal. Beta equals B naught over A. So let's write that down. Hopefully you can see what I write here. So beta is equal to B naught over A. Solving for my constant, I have that B naught is therefore A beta. Okay, now let's set these two equal. Gamma cosine theta and B sub 1 over A squared times cosine theta. So gamma cosine theta equals B sub 1 over A squared cosine theta. Cosine theta and cosine theta cancel out, and so B sub 1 is simply going to be A squared times gamma. A squared times gamma. And so what am I left to conclude? I have my two constants now. I have that B sub 0 is A times beta, and B sub 1 is A squared times gamma. So now I'm going to use this to write out my final electric potential outside the spherical charge distribution. So the electric potential outside the spherical charge distribution is going to be, well, as always, we're going to have V out is going to be the L equals 0th term, which is B sub 0 over R, and then the L equals 1 term, which is B sub 1 over R squared cosine theta. Monopole, dipole. I know what B sub 0 is, I know what B sub 1 is. Now it's just a matter of plugging things in. So I'm going to have A beta over R, A beta over R, plus B sub 1 is A squared gamma over R squared cosine theta. Okay, now let's go ahead and box in our answer, and then there's one critical last step, one last check that we have to execute, and that is whether the electric potential inside and outside match on the boundary. So on the boundary we have that R is equal to A. This is the boundary, and at that moment we must have an electric potential of beta plus gamma cosine theta. Let's see if that's the case. When R is equal to A here, what do we get for the electric potential outside? Is it indeed beta plus gamma cosine theta? Well, V out is going to equal, we're going to have A beta over A plus A squared gamma over A squared cosine theta. Is this equal to beta plus gamma cosine theta? Let's see. These two cancel out, these two cancel out. Indeed, it is beta plus gamma cosine theta. What about here? Well, in this case, when R is equal to A, this A on the bottom and A on the top cancel out, so we have beta plus gamma cosine theta. Indeed. So they do match on the boundary, and they do match the expected electric potential. And the final thing we have to do is determine the surface charge density on the surface of the sphere. Now, how are we going to do that? Well, recall this fact. So let's go ahead and erase the top, and then we'll get to it. All right, folks, so how are we going to determine the surface charge on the boundary? That's where boundary conditions for Maxwell's equations come in. Remember that the divergence of the electric field is equal to the volume charge density over epsilon naught. We can convert this into a boundary condition on the electric field by taking the nabla operator, turning it into a unit normal vector from medium 1 to medium 2. So for instance, in this case, this is medium 1, this is medium 2. Don't take the word mediums too literally. If you're a physicist, don't berate me in the comments, but this is the idea. We're going from space 1 to space 2, puncturing through. And then this is going to be dotted with, dot product stays there. Instead of the electric field, I'm going to have the electric field on the outside minus the electric field on the inside. And this is all going to equal the volume charge density over epsilon naught. Now, I know from the curl of the electric field being 0 that the electric field admits a scalar potential such that minus the gradient of that scalar potential is the electric field. Plugging that over here, what do we get is that the unit normal vector from space 1 to 2 dotted with minus the gradient of V2 minus, since there are two minuses, that makes it plus. One minus coming from the definition of the electric field as minus the gradient of the electric potential, and the other minus coming from this difference. And so we're going to have a net positive sign right here. And this is an electric potential sub 1. And this is going to equal what? Not the volume charge density, but the surface charge density. Why is that? Well, as we shrink our enclosing Gaussian surface into a kind of very small box, then only those charges that are on the surface will be left. And so we're going to have the surface charge density over epsilon naught. And so what will this give us? Well, we can multiply both sides now by this minus sign so as to get the following. We're going to get partial V out partial R minus partial V in partial R. So the gradient of, not the gradient, the partial derivative of the electric potential outside with respect to the normal vector, which in this case is the radial vector r, and the electric potential inside differentiated with respect to r. So we take the difference of those two, and since we multiplied both sides by a minus sign, that right hand side now gains a negative. Okay, so now all that's left to do is take our partial derivatives, right? So let's take partial derivative of the outside with respect to r. So that's going to be as follows. We're going to have partial r of v out, which is this, which is a beta over r plus a squared gamma cosine theta over r squared. And so what is this going to be? Well, this is secretly r to the minus 1, which is going to become minus r to the minus 2, right? So we're going to have minus a beta over r squared. Now, of course, remember, we're talking about surface charge. All of this is happening at the surface at r equals a. So you have to keep that in mind at the very end. After we differentiate, we have to set the radial variable to a, to the surface. So minus a beta over r squared. And here, same idea. Differentiating r to the minus 2 is going to gain a minus 2 a squared gamma cosine theta over r cubed. Okay, now let's go ahead and take the partial derivative with respect to r of the inside. So that's going to actually be considerably easier. We'll have partial r of this, which is beta plus gamma over a r cosine theta. That's simply going to give us 0 for the beta and gamma over a cosine theta for the second term, since it simply has a coefficient of r. And so by taking the difference of these two, we can figure out the surface charge density. So let's do that. So we're going to have, let me erase this big sphere. So I'm going to take the partial derivative of the electric potential outside with respect to r and write it down right here. So we're going to have minus a beta over r squared minus 2a squared gamma cosine theta over r cubed, and then subtract from that gamma over a cosine theta. Now remember, all of this is taking place at the surface, so I'm going to replace my r's with a's. So this r is going to become an a, and this r is going to become an a. Okay, so what am I going to be left with? First of all, on the right hand side, all of this, after taking the difference, is going to be minus the surface charge density over epsilon naught. Notice immediately that all of these minus signs now cancel out, and so we'll be left with a net positive charge for the surface density. So now what am I going to be left with? Now it's just a matter of doing the algebra. So we're going to have a beta over a squared plus 2a squared gamma cosine theta over a cubed plus gamma cosine theta over a. And all of that is equal to sigma over epsilon naught. So we're going to simplify things a little bit, cancel things out. And so our final answer for the surface charge density is going to be, let me write it out over here, multiply both sides by epsilon naught, and that's going to give you sigma, the surface charge density, is epsilon naught times the following, times beta over a, beta over the radius of our spherical distribution, beta over a, plus 2 gamma cosine theta over a, plus 2 gamma cosine theta over a, and plus gamma cosine theta over a. So plus gamma cosine theta over a. And now notice, these two are like terms, so we can just add them up. So this is going to be 3 gamma cosine theta plus beta all over a. So our final answer is going to be 3 gamma cosine theta, right? 3 gamma cosine theta plus beta over a, plus beta all over a. And there you go. That is your surface charge density. Hopefully you learned something from this episode of electromagnetism, and we'll check you out in the next one.